on this computer. Okay, it's probably gonna ask whoever is on Zoom. Okay, is it recording? Did it ask you, Kara, did it ask you to agree
Yeah.
to record? Perfect. Okay, so these lectures, I'm gonna attempt as much as I can to record these lectures, but this is not a requirement, but I wanna do it and I'm gonna make the best effort possible. Sometimes I get a technical problem and I cannot record the lecture, but know that there's a history of lectures available for you all on YouTube, privately listed. You have the links to those on the syllabus on Canvas. So you can go back to any lecture in the past and they are almost identical. There are incremental improvements over the years. But if we miss a lecture, if I am home sick or something, right? So we can fill out the gaps, okay? So today, my objectives today is to first kind of get this COVID-19 discussion started, get it out of our system, and remind you of the policies and all of those things, just like so much information out there. And then discuss the syllabus, some administrative stuff, and then start getting into numerical methods, what you should expect from this course. And we'll talk a little bit about programming. On next Thursday, we'll dig deeper into more discussions about programming. But I want you now to just take a moment and, grab your pen and paper. Don't exist anymore. Maybe pen and paper, and then maybe your tablet, and just write down a couple of things that impacted you negatively, you, your family, your loved ones, really two negative things that impacted you since the pandemic started, and then two positive things that happened to you during the pandemic, and two perspectives that changed in your life during the shutdown, and any other thoughts that you want to share with us. And I'll get some volunteers. I'll volunteer some information myself to kind of share with you. So, for me, a positive and a negative thing is that, so one of the great things that happened is that we actually had a baby, like April 2020, right? That was like 2 weeks into the shutdown. And, it's not like we had a baby because of COVID, right? But we had, we were pregnant, and then the pandemic happened and we had to have the baby in April. But what was negative is like everything was shut down. There were no oxygen. My wife was not allowed to put an oxygen mask on because they're worried about airborne transmission. At the time, they didn't understand how the virus was being transmitted. So that was very stressful. And we went in and out within like barely 24, we didn't even stay 24 hours at the hospital. And they actually botched one of the tests. So they, the test came that my son was not able to hear. And we're like, well, this doesn't make sense. You cannot do a hearing test in the first hour of birth. You got to do it after like 12 hours or so, right? And so, and the nurse was like, oh my gosh, there's so much on my mind going on. And so, everyone was like freaking out and panicking. So that was pretty stressful, but he's fine now. He hears us from a mile away. So, and one of the other negative things was this kind of, so I have two kids, and with kids, like if they're not breaking their arm today, they're like falling, off the stairs or something the next day, and you're like, okay, where can I get medical care for them? And that was very stressful, just trying to find a medical provider. So that thing impacted us negatively. But on the positive side, we got to spend a lot of time with the kids. We got to, it was fun being with the family. I grew up in a civil war, and so I was with my family all the time, pretty much. And so this pandemic was no different in that sense, that, we had to kind of survive together. All right, so let's see. Those are examples of what you might have listed. If you feel, excited about sharing something that impacted you negatively or positively, please raise your hand and let us know. If not, you're not obliged to. I had a student in 2021, they built a house. They're like, oh yeah, we're home, the entire family is at home. They built a house. And I'm like, well, that's great. Well, at that time, lumber was available, I think. So Anyone would like to share something? How it impacted your education, how it affected you? Okay. All right. Well, no problem. I was happy to share my information. Um, the other thing that this thing here about perspective. This pandemic made me think about um, prepping. You hear about these preppers. They're like, crazy forums online. Although my family is a prepper family, again, because we grew up in a war and we had to be extremely frugal in using resources, storing food, etc. And so I could see a problem a mile away. Okay, so before this thing even came to the US, I was at Costco, buying stuff, telling my friends, you gotta get ready. We don't know how it's going to hit us. So, we had stores of food already, but um, what impacted us was with the situation with the childcare. We did not have, because we don't have family here, we did not have a system to assist us with childcare because everyone was fearing everyone else, right? Because anyone could be a carrier, right? And we were not able to get any help with childcare. So, it led us to try to think about a more resilient framework or strategy for the family in case, we go into another shutdown. I'm trying to figure out who can help us, etc. Now, thankfully that we have the vaccine. So, which leads me to this next slide. So, these are recommendations coming down from the university, and I'm hoping for your cooperation. We're, all doing our best to kind of try to get through this because we want to just go back to normal. I personally have an at-risk person at home who is immunocompromised, and so we're all vaccinated and boosted to the wazoo. Like, how many boosters you're gonna get, but still, there's no data available for immunocompromised people. So while, if I get sick, I'm like, yeah, okay, it's probably gonna be I'm vaccinated, it's gonna probably be a like minor illness or so. But, I worry about transmitting it to the immunocompromised person. So I try to be a little bit more conscientious when I'm, around people. And I hope to see the same from others. Vaccines are highly recommended. And so it's, you've probably seen the data, they do reduce the risk of hospitalization. You're still gonna get sick, you're still gonna catch it, just like with the flu shot. You might get the flu, but it's probably gonna last you a day and not too bad of a symptom. So, it's one of the greatest defenses we have with the vaccines. So the university is encouraging everyone to get vaccinated and boosted. Now, in terms of kind of the feeling ill and the being exposed, you're encouraged to get tested. There's like free testing on campus. I owe it to you to get tested because, and I'll show you a study we did just recently on COVID. Technically, I'm the one speaking most of the time here, and I'm the one emitting the most respiratory droplets. Okay, now I have a KN95 mask. It pretty much shields you from all those respiratory aerosols. Okay, but I am the person who, is transmitting the most. And if I am ill, right, I am a critical vector, okay, for everyone in the class. So I owe it to you to get tested. So my plan is to get tested twice a week or at least once a week. That's what I did in my previous class last semester, get regular testing. But, it wouldn't hurt if you do the same. Who knows, maybe your colleague has an at-risk person at home, etc. You want to stay at home, you can stay at home, you can go through Zoom, but I think the experience in person is a higher quality experience. But definitely, if you're feeling ill, whether COVID or not, just let me know. Go get tested. We'll follow the protocol. Stay at home. Even if I have a cold or the flu, I'm like, I stay home a couple of days, and then come back. just, because I don't know who I'm interacting with. So, it would be nice to kind of follow these things. So if you suspect exposure, or if you're ill, or if you test positive, do let me know. Do the self-reporting. I have all of this discussed on the main page on Canvas. So if you kind of forget about it, or if you want to tell a friend who's not at the university, there's a lot of nice resources on that front Canvas page. Excuse me. And if you suspect exposure, follow these guidelines for exposure. There's a contact tracing team, etc. And so many classes from yesterday, today, they've reported exposure. And so, just to let your friends and colleagues know and everyone know. All right. Going over the syllabus and some administrative stuff. So my primary communication mechanism with you is going to be through Canvas. Okay, I'm sure that most of you logged into Canvas and saw the page. Go spend some time reading that, grab a cup of water, a cup of tea, or a cup of coffee, and read through that. There's a link to the syllabus over there. I don't upload a PDF syllabus because my syllabus is organic, it's alive. I update it regularly. It's hosted on a Google Drive. So, you click the link, you'll see the most updated version. If there's a change in the syllabus, you will see it scratched, essentially, with a strike through, and then updated if there's a change in the policy that's going to happen. And we'll discuss that together. But right now, that's how you access the syllabus. There's a ton of information. Go ahead and read it. If something doesn't make sense, come, talk to me. And the way to talk to me is through Canvas email, okay? You can grab the phone and call my office. If I'm not in the office, I'm not gonna answer, but my phone is with me all the time. I get Canvas notifications and I check those regularly. And so best way to communicate with me is through Canvas. There is my other website for old lectures, etc. You don't have to go there. I posted all the old lectures. I put the links to the old lectures on the front Canvas page. They're all on YouTube. You can go see them. You can go through them even before coming to class. And so that will help you. This is an in-person course, and you're expected to attend class. But I understand that, if you are ill, clearly, like we just said, stay home. So we're doing the Zoom thing now. And so you can follow through Zoom. If for any reason there's a complication, there's a challenge where you cannot come to class, just join the Zoom link. And, of course, you're welcome to come to class. Any recorded lectures will be posted on my YouTube channel. There's also a link to that on the main Canvas webpage. These videos are privately listed, so only you can access them. Only those with the link can access them, and that will essentially be just you. Okay. Email. I will communicate with you through Canvas as well. So it's just easier this way. If you can send me an email to my work or private email, but I'm probably not going to get to it. I open my inbox in the morning. I have over 400 emails. Okay. And like, there's no, you are a priority in my life. Okay. So there's my family and then you, right? So, but for me to get to answer you, Canvas is the best way, because when I go to Canvas, I see, 10 emails. I'm like, oh, I better get to this. Right. So, and I know that there's no other emails over there except from the students, except from you. So communicate with me through Canvas. I'll communicate with you through Canvas. So make sure Canvas emails do not end up in your spam folders. Okay. All right. Student hours. I thought this was really cool. I changed the name from office hours to student hours. So it's more student centric, it's more kind of friendly, because these are really your hours, right? They might happen in my office, or they might happen in the library or in a conference room. I still have to decide. But to pick the best hours, I would like you to tell me about your availability. There was an announcement that I sent out like last week about a doodle poll, okay, for your availability. please go to that announcement, go to the Doodle poll, just fill in your availability. Could be anonymous, put your name, I don't care. Just fill out your availability. And then what I'm going to do, I'll pick the best times that optimize for the most availability of students. Okay, so then you can, have regular student hours. You can come in, we can talk, we can discuss what you need, etc. Now we can do this over Zoom as well. Okay, so I will also have a link over Zoom for, those same student hours. You can book an appointment with me. And if you're walking down the hallway, see my door open, just come on in. Okay, just come on into my office. My office and the number and all of this information is on the Canvas page. So always refer to that if you forget, etc. I know you've got like other courses, so much information. So always come to the Canvas page. You're going to find the critical information that you need to get moving. Okay, we will have 4 help sessions to help you with homework and exam preparation. 2 by Jessica and 2 by Adriana. And those sessions are going to be Tuesday, Wednesday, and 2 on Thursdays. Why 2 sessions on Thursdays? Because, from experience, homework is due on Thursdays. And most of you are going to do your homework on Thursday. So we're going to have 2 sessions on Thursdays, because I know that's the time you're going to be crashing down. We used to have a session on Friday, and like my TAs would compete for that because no one came to the session on Friday. So we're doing 2 sessions on Thursdays, and 1 on Tuesday and 1 on Wednesday. The sessions take place in the what used to be called the ICC, the Industrial Computing Center. It's just on the 2nd floor of MEB, the metal engineering, just under the chemical engineering department. Okay, there's a big computer room. Okay, so go over there. These are the session times: 4:15, 5:15 on Tuesdays, 2 to 3. So we tried to kind of mix up the times. I hope you can make them. Oh, sorry, there's some wrong information over here. This is from previous year. Never mind this. So, and also those sessions are available on Zoom. So if you can't make it in person, you can join in over Zoom and have a discussion with the TA, ask your question, etc. Okay. Now, for the help session to be productive for you, come ready. Okay, so work on your homework, work on a problem, and then write down your specific questions. The TAs are not going to spend time instructed by me. They're not going to spend time where you come in and you're like, where do I start? That's not helpful. You got to come start somewhere and hit a block and say, hey, Adriana, what should I do next here? What do you think? And then she'll tell you, what do you think? And you'll tell her, well, I don't know, what do you think? And she's going to tell you, what do you think? And then, oh, maybe I use this equation. And then she'll tell you, well, maybe you have the n wrong over here, how about you try this and that? And then you go and work on it. And then you come. So be prepared. Okay, do not come and just, hey, I don't know where to start. So start somewhere and come ready with specific questions. It will be a much more productive session for you, okay? For technical help and support, this year we're going to be using ED discussion. It's on Canvas. I've never used this. This is first year, so you're probably more versed in it. So you'll be helping us learn how to communicate, but how to use it. But you can use it among each other and help each other. I really want you to cooperate with each other and answer each other's questions. Okay, so that's completely encouraged. Okay, go talk to each other, work on problems together. I don't care. Now, don't copy problems from each other, right? You might get to the same answer, but don't copy kind of the write-up, right? Work on problems together. I really don't care about that. I want to encourage this kind of collaboration. Go on AED discussion and then ask a question. If you have a question, ask it, because Adriana, Jessica, and me are going to check that regularly. Okay, so we're going to check it. We have a cycle where we check it, a certain time of day. And if there's a question and Adriana happens to be checking, or I happen to be checking, or Jessica, then they will answer, or you will answer each other. Okay, it's just like a forum. So let's make it, vibrant and useful. Okay, you don't have to buy a textbook. My lectures have the best of all the textbooks out there. They are sufficient to deliver the content I want to deliver in this class. If you need a reference, grab this textbook by Chopra and Canale, Numerical Methods for Engineers. Get like the cheapest edition you can find on Amazon for like $1 or $2 or $5, whatever inflation is costing right now, right? So it doesn't, the edition doesn't matter. The content didn't change much. So most of my notes are based on that textbook, okay? Except for the Fortran discussions, but it's a very nice textbook, very useful, okay? So if you need a reference, this is a good reference. I will share with you chapters, relevant chapters as needed for additional reading, okay? Like there'll be in PDF format, okay? From that textbook. Okay, in terms of assignments and quizzes, I also changed the word homework to assignment. I should have changed the title. Assignment sounds better. I don't know, maybe. Quizzes, we're gonna be having regular quizzes to test your qualitative understanding of the subject matter, okay? So I might ask you, why is a relative error more useful than a absolute error, okay? And then you either do a multiple choice or write down an answer. Very short quizzes, like 5 minutes. We do them here in class, okay? 2-3 minutes, 2 questions, 3 questions maybe. So, you know, make sure you're kind of ready. And they typically cover material we covered in the previous lecture, okay? We'll have those regularly, kind of out of the blue. So you will also need a laptop or, you know, a smartphone or something just to access. Looks like most of you do. Okay. Okay, perfect. In terms of assignments, we'll have up to 9 assignments. It's going to depend because, again, with the COVID thing, we ended up missing an assignment and a half, I think, in 2020. And so, you know, up to 9 assignments. The assignments will be posted on Canvas, and your submission will be also on Canvas as a Jupyter notebook. We will, does anyone know what a Jupyter notebook is? Okay, there's a few. Okay, for those of you who do not know, you're gonna be amazed. This Jupyter notebook thing is like, no, you're not amazed. Don't listen to, well, maybe your experience will differ this time. So Jupyter notebooks, and we'll discuss this at length later. Imagine you have Microsoft Word, okay, where you typically your modus operandi, your mode of operation is you would write your code in MATLAB or Excel, and you run the thing, you print, you produce a plot, you copy paste it, you produce a Word document, and then you're like, oh crap, I need to change this. You go back to the Excel sheet and you change it, and then you copy paste to Word, and then you convert to PDF. Imagine you could do all of that in one document. You could write your text, you could write your equations, you could write your code, you could generate a plot in one document. And that's what a Jupyter notebook gives you. It allows you to write your text, your discussion, write Python code, generate a plot, refer to that plot, discuss the results in a single document. Makes life so much easier for you and for us. If you might not see this yet, but I hope you see it by the end of the course, okay? Assignments will be assigned every Thursday, and they will be due the following Thursday. Makes everything easy. You know, every Thursday I have an assignment and I have a due assignment. So this Thursday, this coming Thursday, you're gonna have your first assignment, which will be pretty simple. And then it will be due next Thursday, okay? You get, if you have a late submission, 25% daily penalty for late submission. So, you know, you get 3 days. Now, if you have an exception, if you have a CDA situation, and, you know, we work through that. If you have a certain, you know, event happen in your life, talk to me, okay, as soon as possible. Talk to me if you need an extension, and we'll work through that. Typically, you know, I allow a courtesy extension throughout the semester, 1 or 2. And, you know, it's got to be a real situation because we know life happens, right? So I'll be very accommodating that way. And so, but I hope, you know, we will never have to use that. So the solutions will be posted 3 days after the homework is due. So that's kind of the threshold of that late submission. And again, if you need to request an extension, you must discuss this with me no later than 3 days after the assignment is due, is assigned, after the homework is assigned. Assignments will receive some partial credit. And I'll discuss this shortly. I used to have a policy of no partial credit on homework and a lot of partial credit on exams. But that was pre-COVID because exams were handwritten, and every step of the way you get a lot of partial credit. But homework, you go at home, you have time, you got to get something right in your life. So there was no partial credit. But now this changed. So this thing changed. Hey, I'm quoting Richard Felder, who came up with this. He's like a big educator in chemical engineering. And so your submitted Jupyter notebook has to just run as is. So I hope one day you will teach a class as big as this class, even bigger. I used to have 70 students in this class, and there's no natural way on earth I can go through 70 pieces of code, some of them lengthier than the iTunes user agreement, okay? And go through the code line by line and debug it. So before you submit your homework, your assignment, your code needs to run, okay? Make sure it runs. You run it, it runs, produce the result, okay, good, submit. If it doesn't run, we might catch the error very quickly, like you forgot to do an import NumPy or something. But other than that, we cannot debug the code for you, okay? And so you will not receive credit for that. Now then you can probably contest it and say, oh, I forgot this. Could you look at this again? Then we talk through that, okay? But it's best for you to make sure your code runs. So talk to us before you submit. Say, my code is not running. Can you help me? Go to the help session, okay? Talk to your colleagues, okay? Go on the ad discussion, and then we'll sort this through, okay? We will not be able to debug your code. And it's, again, your responsibility to make sure that your notebooks are complete and can be executed without any errors, okay? Now, the first assignment that has Python is going to be a disaster, okay? Based on experience in this class. So we will be accommodating in the first. That's going to be assignment number 2, okay? We'll be okay. We'll work with you to sort out through the bugs and the errors. So we'll be flexible. But then after that, I want this whole process to be streamlined. You will become experts in the errors you see and the errors you've committed in the past, so you don't commit them anymore in the future. Okay, we will hold 3 exams and a final. And actually, your first exam is the Thursday of next week. Now, that might cause you to tremble, but you shouldn't, because it's just a prerequisites exam. It's an exam that tests your knowledge of, hey, can I multiply 2 vectors with each other? Can I multiply a matrix and a vector? Just can I compute this derivative? It's pretty lightweight. And if you have covered the prerequisites, which I assume you have because you wouldn't be in this class, then exam 0 is really 7.5% of the grade handed free to you, okay? There's already an exam 0 study, an exam 0 example, and exam 0 solution to that example, okay, on Canvas. So go and study it. The exam Thursday next week will be about 20 minutes long. It will be on Canvas, so you'll be here, and I'll be walking around. You take the exam, you have your note sheet, etc., and you'll do the exam, okay? So exams might be of the handwritten type or entirely online. I am inclined to do everything online this year, okay? But if they are of the handwritten type, I'll give you, the exam, and then you'll just write it down and do the answers. You'll get a lot of partial credit on that. If it's of the online type, so in the handwritten exam, you get like three, 4 big problems, right? But for the online exams, you get a lot of low stakes questions. It's a glorified quiz, essentially, okay? You will not get any partial credit on that, but you'll get 2 attempts, okay? It's a lot of low stakes questions, like 1 question, 1 answer, right? There's no like lengthy derivations that you have to do, etc. You'll get a lot of questions 20, 25 low stakes questions, okay? But you get 2 attempts, no partial credit, okay? And generally what I've seen is that the students have preferred that over the handwritten exam. Okay, you might say, well, Professor Saad, oh, I didn't say my name. Okay, my name is Tony Saad, okay? And you can call me Dr. Saad, Professor Saad, okay, whatever you prefer, I don't mind. But yeah, that's how it's pronounced, Saad, okay? And if you come to my office hours, I'll tell you what it means, okay? So you might come and say, well, Professor Saad, I'm not good at programming, okay? And, you know, how can I pass the course? Well, the way I structure the course is that the exams have pretty much have absolutely no programming questions in them, okay? So the exams will test your theoretical and just general understanding of numerical methods, okay? Now, on the other hand, homework assignments are heavily based in programming. You need to do a lot of programming to solve the problems. Homework assignments are 25%, and the exams quizzes are 75%. So you can still pass the course with just barely knowing programming. I want you to know programming because it's gonna be, you know, it's gonna make you so much more valuable in the market when you come out. We need to talk with computers, right? It's gonna make you much more competitive. But if you're kind of struggling, then in understanding a theoretical understanding of just theoretical methods, numerical methods, theoretically, how they work, what we're doing, why we use linear solvers, what is the Thomas algorithm, you know, those sorts of things, then you should be okay. And exams are based entirely on that theoretical understanding. There's no like programming questions. I will not ask you to write a for loop, okay? So, you know, that should hopefully kind of relax some of you a little bit, those of you at least who are worried about the programming aspect of this class. Okay, exam 0, next Thursday of next week, cover prerequisite. So all exams are closed books, closed notes, but so exam 0, 1, and 2, you get one double-sided letter size sheet. And the exam 0, 1, and 2, well, exams 1 and 2 cover only recent material. Final exam is comprehensive, and you get 2 double-sided letter size sheets, okay? Now, I will give you complex equations. So you will learn things like, you know, the Gauss-Seidel iteration. I will give you the formula for that. I don't expect you to memorize it, okay? I will give you the formula for that. I will ask a question and I will tell you, recall that the Gauss-Seidel iteration looks like this, okay? So don't worry about that as you put your note sheets together. Your note sheets should focus on kind of the critical understanding, the things that we've discussed in class where, you know, there's always an exception to this, an exception to that, okay? And whatever you want, really. But, you know, make the font readable. I don't want you to get like magnifying glasses to be able to read your note sheet. You know, you can typeset it, you can handwrite it, I don't care, okay? Okay, here's the partial credit policy for the homework assignments. If the method is correct, no errors, then you get 100% credit, okay? If the method is correct, but contains an arithmetic or minor programming error that we can immediately spot and fix, then you get 20% off, well, you get minus 20% per error. Okay, so for example, if you had a typo in one of the factors, although your formula is correct, let's say, you know, you're calculating the sample mean versus the population mean, for example, and then your formula is correct, but use the wrong number in the calculation, then you'll get docked just 20%, but that's per question. So the next question, whatever value you got in the previous question, we assume that's true and you'll get full credit on the question that follows, okay? But you gotta get it right. So that's why in your homework, you know, focus, get the answer right, check with your colleagues, be critical, be a critical thinker, whether your answer makes sense or not, okay? The solution contains a minor theoretical error. So theoretical errors are more dangerous than arithmetic errors. Because an arithmetic error, you can just kind of spot it. A theoretical error means you did not understand the subject matter. So a minor theoretical error is more expensive, so costs you 40% per minor theoretical error. And that's really the only two errors we see, either arithmetic or a misunderstanding of the subject matter. Okay, all other errors, essentially, you get no credit. Now, for exams, again, the policy, if it's handwritten, you get a lot of partial credit, but for online exams, you'll get 2 attempts, no partial credit, because the question cannot even afford partial credit. It's either a yes or no, right? So there's no like maybe. Okay. This is currently the percentage weights for the assignments and exams. So assignments are 25% of your total grade. Exam 0 is 7.5%. So get ready for it. 2 midterm exams, 35%, quizzes 7.5%, and the final is 25%. Okay. Now, I know you want to get a grade to pass, to stay in the program, etc. And I understand that. But I hope you can look beyond this. You can look to improve yourself, your knowledge of numerical methods, of programming, of learning. This course has a lot of examples in chemical engineering and engineering. By the end of the course, you are going to develop a model for the COVID-19 pandemic. And it's going to be awesome. And this doesn't take that much advanced knowledge to do a prediction of what's going to happen in the pandemic and what happens when a vaccine is introduced. We use ordinary differential equations to do that. And we do the analogy with chemical kinetics. But, I hope that you can see beyond the grade to say, look, I know I want to pass this course, but I want to put that aside. And I want to try to learn a few things here in this class. Okay, I hope I don't fail the class, but what is more important is to be a critical thinker, okay, about science and engineering, to be a better communicator in your assignments, and really a critical thinker. That's a critical skill that you need to develop, okay, and then a problem solver. So I hope you can see that. All right. So with that behind us, let's kind of get a little perspective on numerical methods. So we're still doing good on time. Okay. So as you learn in engineering and science, there are these things called the grade conservation laws. Who's heard of a grade conservation law? Who can give me an example of a grade? Yeah. Yes, what's your name? Trent. Okay, conservation of energy. What else? Yeah. Yes. Okay. So conservation of momentum essentially says if you have, like 2 cars colliding with each other, their momenta are gonna be conserved, and that's gonna be transferred to destroying the vehicle and potentially, doing harm. What's your name? Matt. All right. What other conservation laws can you think of? Yes. So what does it tell us? Conservation of mass. Yeah. Yeah. So mass is conserved. If you have, that's why when you're watering your beautiful garden, in the short Utah summer that you have, my summers are very short and sandy, so barely get, 6 weeks of growing. But, when you grab your water hose, there's water coming out at a certain flow rate. What happens when you close it a little bit with your thumb? Shoots out faster. Why? Because it needs to conserve mass. The mass that was going in with the big opening, when you close the opening, to conserve the same mass coming out, it must come out faster, right? To produce the same flow rate. So that's conservation of mass. So these great conservation laws are really the foundation of physics and engineering and the sciences, okay? And that's what you will be learning in chemical engineering, okay? As you go through your courses, and this is what you will be learning: conservation of energy, mass, and momentum, okay? And then we have these approximations and models that model these conservation laws. So Newton's law is a statement of, conservation of momentum, okay? Mass and fluid mechanics, you have also conservation of momentum, conservation of mass, conservation of energy. And we have models for those, and these are essentially the equations that govern these conservation laws. And as you go through your courses, you're gonna learn about techniques. We call this algorithm because now we're in a numerical methods mindset. A set of steps to get an answer. You do this, you do that, you draw a rectangle around the subject, around the object, and you calculate the forces, and you get an answer. That's called an algorithm. And probably in 1703, or what you've done so far, is you would probably either solve it by hand, or if it's a little bit more complicated, you use some more advanced numerical tools like MATLAB, Python, or Excel. Okay, that's kind of a general perspective of engineering, how the engineering process works. So this was over here, 1703. Okay, that's kind of what you learned. You were focused on just learning the tools. Okay, 2450 is here. This is 2450. Okay, we're gonna go one step deeper. Now, after 2450, you're gonna learn the conservation laws, how to derive them, and how to develop the models and approximations. In this class, I will give you the model and the approximation, okay? And we'll develop the algorithm together on how to solve that model and approximation. Okay, perhaps what would be more kind of motivating to you is to show you this in practice. So I run the multi-scale simulation groups at the University of Utah here in chemical engineering, in collaboration with Professor Sutherland, whom you will encounter in a few years. Okay, my group is called the Utah Computational Engineering Laboratory, and I want to give you here just a little perspective of where numerical methods and where my research fits in. So my research is in numerical methods, okay, specifically applied to fluid dynamics problems. But the standard scientific method has these 3 steps in it. First, you make an observation, things fall to the ground, right? Or there's a spike in COVID cases, okay? Or there's an outbreak over here. You make an observation. This is interesting. It's an observation. Then, based on either further observations, your knowledge of things, of physics, okay, you make a hypothesis. If you didn't connect the dots, things falling to the ground, that's the dramatization of what Isaac Newton, what is told about Isaac Newton, how he discovered his famous laws, okay? So Newton made a hypothesis that, well, things fall to the ground, things keep falling to the ground, wherever you are. So there must be this mysterious thing we call force that attracts these objects to the ground. And he developed a hypothesis. And he said, okay, I hypothesize that there's a mysterious force that pulls things to the ground. Now, my hypothesis mathematically looks like this force is proportional to the mass times acceleration. Why did he come up with that specific form? Because he based data on what Galileo was doing, you know, a few years before him, okay? Now, with the hypothesis, okay, it should explain what's been observed, and it should make a prediction. So that's the hypothesis test. So after the hypothesis, you design a bunch of experiments. So drop things from a tower or go drop things and see if the force is indeed mass times acceleration. And if you find something wrong, then you go back, you refine your hypothesis, and then run an experiment, and then do hypothesis, refine your hypothesis until you come with a theory. So be careful when someone says the theory of something, it doesn't mean this is still theoretical. The theory is actually the result of the scientific method. It's when a hypothesis has been made, it's been tested to be true, then that becomes a theory. Okay? So I know colloquially we used, in theory, this should happen and that, but that might not be true. No, in science, a theory is something that's been tested. A hypothesis, on the other hand, is something that might or might not be true. Okay, so make sure you see that distinction. But okay, so this is great. But how do you do an experiment on an exploding star? It's very dangerous. Okay. So how do you study an exploding star? How do you experiment? What if there's no supernovas anymore in the observable universe? Okay, or you see a bunch of supernovas, which are exploding stars. Okay, and okay, you make a hypothesis and then you want to test it, and like, well, how do you do an exploding star in a lab? It's probably also illegal. Okay, how do you experiment on a hurricane? I mean, there are some hurricane models using kind of water with these small scale, but it's like it's it's kind of it feels like you're not really doing the full experiment of a true hurricane. How would you experiment on nuclear accident? I mean, like, what do you like? You go and hurt people with a nuclear, go stand over there, we're gonna have a meltdown. We put a bunch of raccoons or something. That's like unethical. That's not, you can't do that, right? You can't do that. Something a little bit more, I mean, less ominous than the other ones. Like, how do you experiment on a coal boiler? These things are hot. They'll probably melt down all your thermocouples. The best you can do is take a couple of pictures of it, like take some measurements, and it's not going to give you the full picture. And a bunch of other things. There's this process called precipitation. If you've ever been in one of those underground caves, you see these beautiful calcium carbonate formations. Those take thousands of years to form. Okay. Those take thousands of years to form. How do you run an experiment? So I'll start the experiment today, and then, my grandchildren will collect the data. There's no way to do that. So this is where simulation comes in, and where numerical methods really come in. It's a new kind of science where we've augmented this scientific method by taking an experiment where the role of the experiment now becomes limited to identifying aspects of a big complex system. So we no longer really need to experiment on an exploding star, but instead we can run some data on getting some properties, of exploding stars. Like, we know when we know the heavier elements, all the elements heavier than iron actually are formed in supernovas. So stars, they run nuclear fusion. I don't know if any one of you is interested in astrophysics and astronomy, but stars, they are the universe's materials manufacturers. So they fuse hydrogen and then helium, and they build heavier and heavier elements. But once they reach iron, they can no longer fuse. You need stronger forces than fusion to fuse elements heavier than iron. So what happens, a supernova happens when the star becomes big enough where it cannot sustain itself. It explodes. And in that explosion, it fuses iron with other elements and creates all the heavier elements. Yeah, I mean, thankfully, we are here thanks to that process, right? And so you run an experiment, you get a property, for example, you develop some basic laws. All right, so we understand now that the hydrogen and the helium interact this way, the helium and oxygen interact this way and that way. We put all of those together, put them in a model, we run a simulation. Now you can simulate an exploding star. You can simulate a coal boiler, you can simulate a hurricane. And then if it doesn't match your observations, you refine your models, okay, and then run the process again, okay? So that's where simulation comes in. And simulation, everything in simulation has to do with numerical methods. So these are some simulations from my code here at the University of Utah. See, user T Saad, that's for me. That was a few years ago. We were running a simulation on a coal boiler. So this is coal being injected over here. It gets kind of sort of aerosolized. Well, not aerosolized. Well, yeah, sort of. I mean, they're like little coal particles. They get floated with the gas, and then it kind of mixes up. Now, what's really cool about this is that if I take this plane over here and climb on top and take a picture, okay, this is what it looks like in real life. It's called the fireball, okay? And this process is so fast that even if fast shutter speed, you know, couldn't even capture the structures. It kind of looks a little bit like cotton candy average. Now look at the result of my simulation. It's getting started, and then the fireball gets starting to form. Look at that. I not only have the general pattern that's observed in reality, I have at every instant in time and every point in space, I know the speed, I know the temperature, I know the pressure, okay? No more thermocouples or any of that stuff, okay? And that helps us develop more efficient boilers, okay? These are some simulations all made with numerical methods. Some of those are have tangible applications. Some of those are just research related. This is another problem where you're actually tracking here a helicopter emitting a sound, and we were trying to kind of, this was a subcontract with the military to kind of try to find, develop a method that is fast enough where a helicopter pilot could run a bunch of simulations to see the best path to approach a certain territory with minimum sound emissions, okay? Most importantly is the work we did at the beginning of the pandemic in the summer of 2020. In June 2020, I remember I was sitting outside, you know, reading and studying. No, I was just sitting outside looking at the beautiful sky. And then we get this email and then phone call from the former president of the University of Utah, Professor Dave Pershing. He is a faculty in our department, okay? And apparently he has some contacts at the Utah Symphony, and they reached out to him seeking advice if they can come back to perform, because if you look at the economic impact of the shutdown and COVID, the performing arts have been hit really hard. Imagine singing, you know, that's like a critical pathway for emissions, right? And wind instruments, playing in an orchestra. I mean, a string instrument or a pianist, a guitar player, they can mask up, right? But a wind instrument, a flute player, a bassoon, a trombone player, you know, you can mask them up, but it destroys the acoustics, right? And so they asked us to see if we can find a way to understand what their risk is here at Abravanel Hall in Salt Lake City and Capitol Theater. So if you've never been, who's been to the Utah Symphony? One of the, oh, wow, I have a lot of music connoisseurs. Okay, so which one have you been at? Abravanel Hall? Yeah, okay. How recently? Okay, okay. Way before, okay. Well, they recently had like this, they had this Star Wars theme thing going on. It was pretty cool. Anyway, so they want to understand what's going on. And we did all of that for them. It took us about 6 weeks to do the work. It was really crunch time at the time. But what you're looking at here are two sets of results. Now, forget the results to your right. Okay, focus on the results to the left. This is the baseline configuration of the Utah Symphony. Each one of those cylinders is a player, is an instrumentalist. The front row are all string instruments. You can see the piano here. You can see the drums in the back, and I think the harp in the back here. But all of the other ones, you see these little funnels in front of them, they are wind instrument players, okay? The trumpets are over here, those two guys, really bad. The flutes are over here. You see why this is a flute? It's got two openings, right? There's the opening at the reed and opening at the end of the instrument, right? So you get two emissions. So what we did, we said, okay, how can we model COVID for an orchestra? Well, it all boils down to tracking aerosols that are being emitted by a person. So once we knew what the particle emissions, or how many respiratory droplets are being emitted by different wind instruments, then we could put this in our fluid dynamics simulation code, okay, and then track these aerosols. So the colors show concentration, particles per liter. If you look at this scale, red is 100 particles per liter and more, and white is kind of between 1 and 10, so I would say about 5 particles per liter, and dark blue is less than 0.1 particle per liter. So most of the stage over here is pretty much contaminated by aerosols. So now maybe one of them is infected, maybe they're not all playing at the same time, it doesn't matter. We looked at the extreme case scenario. If they're all playing together, you know, this is a no-go. Okay, and you can see the 3D simulation up there. Same thing with the colors. The red is 10 particles per liter, orange is 1, and yellow is 0.1. Because as the particles are emitted, they get diluted, right? So the color changes. What we did here, so, you know, we studied this. We thought, okay, how can we alleviate this? You notice I had the door open over there, and I couldn't get this door open, but next week it will be open, next Thursday. First thing we did, we opened the doors on the stage. Why? What would you do if you were driving an Uber and one of the passengers was smoking? Or you were riding with someone, you know, who was smoking for some reason. You have a van, right? Let's say you have a van. What would you do? Because you don't like the smell of the cigarette smoke, okay? Or, you know, you don't want to be exposed. What do you do, really? Okay, open the window, blast the AC. Okay, great. That's why I have the door open. We'll open that door again. Why? You want to bring in fresh air and get the contaminated air out of the way. What else could you do if you have a van? Go back, dude. Go sit way back. Okay, so this is exactly what we did. Notice what we did here. All the string instruments are front. We brought the drums, the harp, the piano, we put them in the middle, and we pushed away all the wind instruments. We put them closer to the windows. So there were return vents in the back. We opened these doors. These doors were produced a huge airflow. Look at that. Look at the simulation above. And see the reduction in particle accumulation that we created just by doing this. So it started like, how can a chemical engineer help with COVID transmission? Well, once we knew that COVID is an airborne disease, then it's a question of fluid mechanics, right? Because to infect someone, that infected droplet needs to be transported from the source to the destination. And the only mechanism on Earth that this happens is through airflow. So bam, fluid mechanics problem, simulation. And to test this, we went there and I went up on stage. I took off my mask. I was like, I am comfortable here. No vaccine at the time. Okay, none of that. But then the county are like, you cannot do that. You know, you have to put your mask on. I was like, okay, I'll put the mask on. Okay, you can find a bunch of things. There's a KUR interview about this and a bunch of articles, Andy, many others. Okay, there's also a bunch of, on my YouTube channel, you can find the full discussion and, you know, presentation on the work, etc. Okay. All right. So, but all of this simulation that I showed you actually is no different than what numerical methods is about. Okay, you need to know math, you need to know numerical methods for simulation, you need to know programming or computer science, some computer science, and you need to know your engineering, your physics. Okay, so you need to be a polymath. And that's great because that's the world we live in now. Okay, and that's, I hope, what this course is going to start getting you in the mindset of that. Yeah, I need to do all of those things. You know, don't let the discipline define you. You define the discipline. Okay? Chemical engineering is not just about chemical engineering or process engineering or petroleum. It's about anything, really. Are you going to tell me that if you discover a cure for cancer, you're going to say, oh, darn it, I'm a chemical engineer, I cannot publish this, I'm going to throw it away? Right? That's ridiculous. Okay. All right, some survival tips in this class. Unfortunately, this class is not about programming. I would have loved, if this class was about programming, I would have loved to teach a full course on programming, but there's just not enough credits, not enough time to teach you programming as well. So I do expect you to ramp up on your programming skills. And we're gonna start slowly, okay? I'm gonna help you as much as I can, but you have to put in an effort to cross that initial barrier of what you need to do for programming, okay? Now, the goal of the course is numerical methods, and programming is only a tool, okay? That's how I look at it. And I'll give you some tips about how to approach the programming. There's a lot of discussion on programming. Now, however, to do serious numerical methods, you need programming. It's just a calculator, okay? It's just a very fancy way of helping you solve your problems. That's what programming is. So you will need to brush up on your programming skills right now, because we use programming extensively. I will introduce Python to you, and we will work together on improving your skills, okay? And teaching you tips and tricks to get better. My objective, I don't want you to write the Shakespearean equivalent of code. Okay, I want you to write code that works, right? You're gonna have enough time in your career and life to become a better programmer. But my concern is that my objective is that you learn how to think about a programming, okay? Start on homework early, okay? It's not high school. So it would be nice if you review class notes prior to the lecture. So I will post all the lectures before class starts, okay? Now those lectures are also organic and alive. If I find a typo, I'm gonna go and change it. So always refer to the latest version of the lecture. I know you might take some notes on your lectures. So, if you find the new version has fixed a typo, just, highlight it. They're not gonna change significantly, okay? But they will be regularly updated. But I will post them before our discussions, okay? So you can get to them, look at them, see what you're up against, okay? That's very helpful. Before doing homework, I suggest you rework all the examples we did in class. And if you're stuck, get help. So I'm happy, we're all happy, the TAs, myself, we're happy to answer your questions. Talk to each other as well. But, we're not gonna do the work for you, okay? We're not gonna do the work for you. So don't get frustrated. Please don't get frustrated. I know it's gonna take an effort. It's not an easy class, but it's not a hard class either. With the right ingredients, you can get through it, and you'll have a tremendous learning experience. Okay. My objective is for you not to get the answer, but for you to critically think about the answer. So we used to have handwritten exams and time is running out, I tell students, look, you get an answer, and if it doesn't make sense, tell me this answer doesn't make sense. Okay, so for example, you take two spheres in outer space. One sphere is at 1,000 degrees and the other one is at 10,000 degrees. And I ask you to calculate the temperature in the middle, and you get 15 million degrees in the middle. It doesn't make sense. Where did this energy come from, right? Probably you had an error in your Boltzmann constant, okay? That's actually a real example for me for heat transfer. But I told my teacher, this doesn't make sense. I got full credit for it, okay? Because the objective is not to get the answer right, it's to think critically about the results that you are seeing, okay? That is more important than just getting the answer, okay? writing code is not the goal. So again, I don't care if you write Shakespearean style code. I don't care if it's 1,000 lines, as long as it gets the answer, okay? Now, how you present your results is often as important as the results themselves. So, you know, but that's kind of more of a longer term objective for you in your career, is to be a better science communicator, a better communicator of the findings that you've discovered as you are working for the company or working at a university, etc. Okay, now some time on programming. Many people get hung up on the programming language. So you've probably done Python. Who's done Python? Who's done MATLAB? Let's see. Python? Python? Okay. Okay, love it. Great. Who's done MATLAB? Okay. So we'll help you transition from MATLAB because, you know, all the data is pointing out that Python is the future, probably for the next decade or 7 years, and then you have to learn another programming language. Darn it. But guess what? It doesn't matter, because if you learn to think about how to solve a problem, then the language doesn't matter. Who speaks more than one language here? Wow, great. How many languages do you speak? 2. Okay. 2, 2, 2. I speak 3. Okay, but let me ask you this. Can you express the same thought in the 2 languages you speak? Yeah, I can do the same, right? I can express the same thought in many different languages. And this is exactly how you should think about programming languages. The thought is, how do I solve a problem? How do I to solve this problem, let's say, I need to first create an array of X points, and then I need to create a for loop to take the square of each point, and then I need to plot it. That's the thought. Now go take that thought and express it in French and English, Spanish, Chinese, whatever. Express it in MATLAB, Python, C, C++. That's what the programming language is. If you know the thought, then it doesn't matter what language you implement it in. Because guess what? You can just go and Google it. You can just go and say, how do I do a for loop in Python? Okay, great. Let's do it. How do I do a for loop in C++? You just go and do it. Okay? But what's more important is to think that thought. What do I need to do to solve that problem? Using a computer language. It's called a language because of that. It's just a language. It's just if you want, it's just the clothing around the thought. That's what the language is. Now we choose the Python language because it's kind of nice and hip right now. Eventually, it's not going to be hip anymore. And there's going to be another language that's going to replace it. But it doesn't matter, because you would have developed at that time the ability to think about how you want to solve your problem. Okay? Okay, so the language should not be your concern. That's the thought I kind of I just expressed. So now, why Python? Because it's free forever. I like free things. I mean, you know, eventually someone has to pay for something, but many of these efforts are a result of, you know, community, and they produce significant, like, you know, the courses being taught on Python, that's a lot of revenue generating thing. But Python is a free language. The distributions are free, which is great. You don't have to pay for your MATLAB licenses. You don't have to worry about that. Okay. It is very easy to get started programming with Python. Okay, you probably know that because most of you are already doing some Python. And it's in very high demand. I'll show you a slide in the next set of slides where it ranks Python actually #1 on the IEEE Spectrum magazine in terms of job demand. I mean, you can use it for web application development, real estate, scientific numerical analysis, scientific computing, all of that stuff. It's a great programming language to know, okay? And Python is very forgiving. You're like, okay, let me add apples and oranges. Oh, it's going to give you a watermelon. You're like, okay, that's weird. But it lets you do it, right? It doesn't barf at you. And most of the time when you play around with these things, it just works. So just try it, okay? It just works. It's very forgiving that way, and I love it for that. Okay, and there's a significant community support around Python. You know, Google, Stack Overflow, a lot of forums and websites out there. And the best part is you don't need anything more than a laptop and an internet connection. Okay, so we've worked hard with the Center for High Performance Computing to develop something called Jupyter Hub, which I'll share with you next Thursday. So that all you have to do is go to the website ondemand.chpc.edu, and you have Python in front of you. Nothing. You don't have to install anything, no licenses, no kind of libraries and all that stuff. Okay, so we remove the transaction barrier from in front of you to get to actually do programming. Okay, and I use Google to learn Python, so you know. All right, so there are two ways that we will access Python in this course. I really don't care which one you choose, it's up to you. You probably have a Python installation on your laptops. Great. If you don't, I want you to go and sign up for an account at chpc.utah.edu and use the following information for class, Command 2450, and just copy and paste this token. And you will get an account at the Center for High Performance Computing at the U. And then we will talk about what you will do with that information later. Then that will allow you to access Python in your web browser. Now, for those who have local Python installations, are you using Jupyter Notebooks or just like PyCharm or Spider or something else? A little bit. So, but you have access to Jupyter Notebooks. Okay, great. That's great. Perfect. Okay, this will become clear for those who didn't understand a word I said. Okay. All right. Now, again, it's your responsibility to learn Python. I will help you pick up tips and techniques, and I will give you the heavy-duty code. In the past, I used to ask students to write the entire algorithm, for example, for the Gauss-Seidel iteration. I don't do that anymore. I just give you the code, the function, but you will be responsible to know how to call that function. In other words, you're responsible for the thought. We're gonna cook a lobster or an eggplant in this class, not virtually, I mean, so on the slide. So we're going to develop a heat transfer model. And in that process, you're going to say, okay, I need to create an array, and then I need to build the linear system, and then I need to solve the linear system using Gauss-Seidel iteration. I'll give you that code, but you're responsible to know where and when you need to call that code. So that's really not that hard when you think of it this way, okay? It's just the thought of the structure of what you need to do to solve the problem, okay? And the syllabus is full of resources to learn Python. And it's also posted on the Canvas page. Your first assignment is going to be to go over these slides linked here. Okay, this is a set of slides that I created to just kind of get you started with Python. If you know what those are, then cruise through those slides and, call it a day. Okay. Just a short discussion here on kind of solving problems, and this will be part of everything we do. You will, if you struggle on how to solve a problem, there's always a rational way to do this. And first, you define what you know and what you don't know. Okay, then you write down a solution procedure to try to get to what you want. Don't forget your objective. In this question, I have to identify which gas station cheated us in their, rounding up or rounding down of the, meter of the gas mirror. Okay, something like that. So don't forget that in mind, and then write down what you need to do to get to that point. And for each one of those steps, you write down sub-steps for what you would need to do. I know this seems like very far-fetched now, so we'll get to experiment with this together in class. And then you plan your numerical implementation. Essentially, is if you need multiple functions to solve a problem, test each function individually. We will talk about verification at some point in the class. When you have multiple things that you need to use a function that solves the linear system. You need a function to calculate the integral. You need a function to calculate the derivative. You don't just put them all together without testing each one individually. Instead, you test each one individually, make sure it works, give it a check mark, the QE passed, QC passed, quality control. Okay. And with that, I'll wrap it up for today. right on time. Thank you so much for your attention. Okay. Fill out the student hours doodle poll, please. Okay. Thank you.